Hello and welcome to the Further Maths Support Programme revision recordings for A-level modules. In this session we're going to be looking at MEI Mechanics 2 and particularly looking at the force section of this specification. So these are the main points that you need to be aware of. You need to understand that bodies in contact may have a frictional force applied as well as a normal contact force, and you need to be able to draw the force diagram to show that clearly. You need to understand frictional force can be modelled by F is less than or equal to mu r, and you need to be able to apply Newton's laws to problems involving friction. You need to be able to make calculations involving rigid bodies in equilibrium. So first of all, by drawing a force diagram for that rigid body, including all of the forces in that system. To be able to understand that a system of forces has a turning effect on a rigid body. To be able to calculate the moment about a fixed axis of a force that acts in that body. To be able to understand the conditions for the equilibrium of a rigid body and to be able to use that to solve problems, and to be able to identify whether equilibrium will be broken by sliding or toppling in some simple cases. Finally, you need to be confident on the frameworks techniques. You need to be able to find the internal forces in a framework of light rods by applying equilibrium conditions at the joints, and you also need to be able to determine which rods in a framework are in compression and which are in tension. Okay, so we're going to start off with an exam question example here. If you want to work through this yourself before seeing the solution, then pause the recording at this point because I'm going to start going through that solution right away. So we have a cupboard on a horizontal floor. It has this base, CE, vertical ends, BC and DE, and an overhanging top AD here. The dimensions are shown in the diagram, and the cupboard and its contents have a weight of 340 newtons, and the centre of mass of the cupboard has been located here at G. It asks you first of all to calculate the magnitude of the vertical force required at A for the cupboard to be on the point of tipping, and it asks you to do that in two different cases. So we're going to go ahead and work on the first of those now. So if we want the cupboard to be on the point of tipping with the force acting downwards, let's draw that force in. So the force at A here is what we're looking for. I'm just going to call that F. I'm also going to put in the weight of the cupboard acting through that centre of mass that we know is located at G. And I'm also going to add in a couple of other forces here. When the cupboard is on the point of tipping, it's going to tip around this point C here. That will be the pivot point. So I'm going to show the reaction force, the normal reaction at that point, acting upwards. I could also consider whether there's going to be friction in this case, but because I can't see any other horizontal forces in this particular question, I'm going to assume that no friction is relevant in this question. Okay, so if I'm trying to find the magnitude of F, I could resolve vertically, balancing the forces, but that would bring this unknown reaction force, the normal reaction here, into play. So ideally, I want to avoid anything that will involve using R, which I suggest means that the ideal method here is to take moments about C. Because R acts through C, we can ignore it when we take moments. And then we just need to equate the products of the forces and their perpendicular distances from the centre of rotation. Sorry, the perpendicular distance of their line of action from the centre of rotation. So F is at a distance of 0.125, and the 340 newtons acts at a distance of 0.5 from that centre of rotation, and if we rearrange that, that gives us F equals 1360 newtons. You notice here that it's irrelevant how high the shown foot of these arrows is. This one is down here, this one is up here. Because they are both vertical forces, we can just take that horizontal distance as being the perpendicular distance of the line of action from the pivot in that case. Marks for that one, a method mark for the moments, particularly moments about C, including all the forces with no extras, an answer for getting the answer mark for getting the distances correct, and an answer marked for a correct answer only for the 1360. Okay, this time we're going to have the force at A acting upwards, so let's change it to be F1 acting upwards. We still have our 340 newtons acting downwards here. if the force is acting upwards, I would suggest that the cupboard is about to pivot about the point E here. So we can show our normal reaction acting upwards at point E here, and we can do the same technique again. This time we're taking moments about E instead of C, and this is going to give us our F1 multiplied by the total distance of the line of action from E, from the axis. That's going to be 2.125, and that's going to be equal to 340 multiplied by its distance from the pivot, which is going to be 2 meters minus 0.5 meters, so 1.5 meters, and this rearranges here to give our new force as being 240 newtons. Notice that that's quite significantly less than the force required to turn it about the much closer axis. And the mark scheme for this section of the question is exactly the same as in the previous one. Okay, so we're now moving on to extend that question a little bit further. I'll just, if you want to pause and just read through that part of the question, that would be great. But we now have the force that's applied at A acting at an angle to the horizontal here, and we're given the trig ratios that describe that angle. We have to consider the vertical and horizontal components of the force A and show that the moment of the force about E is 30q over 13. Now part of this diagram has been removed, so on the next page I'm going to just add a little bit of diagram back in. Okay, so let's just go ahead to the next page and take a look at that. So we've got to show the clockwise moment of this force about E is 30q, etc. So I'm just going to show the vertical side of the cupboard here. So this is E, the point that we're going to take moments about. This is distance 0.9, that was defined on the first slide. The total distance across the top here is 2.125 meters. And we have our vector Q coming in here, and this is the one that we need to find our moment for. So looking at E here, I think you can see that Q could be split into two perpendicular components. I'm going to take one component that goes horizontally and one component that works vertically to replace my Q here. This horizontal component is going to be given by Q cos theta, just using a little bit of trigonometry in this section here. And this vertical component is going to be given by Q sine theta. And all we have to do to find the moment of Q then is to sum the moments of those two components. So my total moment here, moment about E, is going to be equal to, and I'm going to take this in a clockwise direction. So Q cosine theta has a perpendicular distance of 0.9 meters from the pivot, so it's going to be Q cos theta multiplied by, I'm going to write it as 9 over 10, so I've got a fraction I can simplify, and we're going to add to that the clockwise component of the Q sine theta component, and the distance of that from the axis is the 2.125. 0.125 is an eighth, so this is 2 1/8, which I make 17 over 8, I think, as our fraction version of that distance. We can substitute in our expressions for cos theta and sine theta, so 5 over 13 times 9 over 10 and 12 over 13 times 17 over 8, and a little bit of calculating on that does indeed get that to reduce down to 30q over 13. Marks for this one, there's a method mark for the moments expression, there's a B mark for getting correct lengths or ratios, and an E mark for getting the shown answer. Okay, we've now got to show that Q is 221, so the force of magnitude Q is acting, the cupboard's in equilibrium and is on the point of tipping, but not on the point of sliding. And we're going to need to find the value of Q then and show some information about the coefficient of friction. Again, I'm going to need to just put a bit more information onto the diagram here. This is E. If it's on the point of tipping around E, then we've got our reaction force can be considered to act at E. We're going to have a frictional force, and the frictional force has got to act right to left because the only other horizontal force in the system is this component of Q in the horizontal direction. So that's going to be necessary in there. I'm also going to add in, I'm sorry this crashes over the print here, but I'm also going to add in my centre of mass here and my weight acting down. So we said in the first part of the question that the weight here was 340 newtons, this horizontal distance here 1.5 metres, and this is my 2.125 metres here, and this is my 0.9. Okay, so we've got enough information here to be able to calculate the value of Q. We know the clockwise moment of Q is this 30Q over 13 that we saw previously. That's going to have to equal the anti-clockwise moment produced by the weight here. So 30Q over 13 is the clockwise moment about E. Let's just say that we're taking moments about E here. That's going to be equal to the anti-clockwise moment, which is 340 times 1.5 for the weight, and a little rearrangement on that does indeed produce Q equals 221. We then want to find the coefficient of friction between the cupboard base and the floor, and we have to show that it's greater than 5/8. Again, apologies for crashing the text there. In order to find that coefficient of friction, we're going to need to find R and F here so that we can use F is less than or equal to mu R. So we know that it's not on the point of slipping, it's on the point of toppling. So actually we're going to use the strictly less than version. We know that F is less than mu R in this particular case. But we still need to find expressions for F and R. So let's resolve. Balancing forces, this is our other technique that we can use here. Resolving the vertical direction. Upwards we have R and our component of Q, so Q sine theta. And downwards we have our 340 Newton weight. And a little rearrangement on that gives you R is 136 newtons. That's just using our value for Q that we know is 221 and our value for sine theta and rearranging. If we work in the horizontal direction, the horizontal forces are F and the horizontal component of Q, and those must equal each other. So F is Q cos theta, which means that F is 85 newtons. We know that F is less than mu R, so 85 is less than mu times 136, so mu is greater than 85 over 136, which does indeed equal the 5/8 that we were asked to demonstrate. Mark scheme for this one. When you take moments here, there's a method mark for moment equation containing all of the right forces, and an E mark for getting the value that was given. In the second part of the question, you've then got a method mark and an answer mark for calculating R, a method mark and an answer mark for calculating F, a method mark for using F is less than mu R, and an E mark for showing that mu has to be greater than 5/8. Okay, so now we're going to take a look at a frameworks question. Again, if you want to work on this yourself before seeing the solution, then please do go ahead and pause at this point and read through. The actual question part is on the next slide, so please read this text and then go to the next slide, and I'll be following that up with an explanation. So here is the remainder of the question, and I'm going to be working through each of the sections of this question in the following slides. Okay, so first of all we have to show in this situation that T is 600 and calculate the values of X and Y. Okay, well, in order to do that we need to look at these external forces that are going on in the diagram here. I would suggest if you're trying to find a value for T, you really want to be able to avoid anything that uses X and Y, because at the moment they are unknowns. We're going to do those in just a second. So ideally we're going to have to take moments about A, because that avoids X and Y, because they both act through that point. So let's take moments about A. And although there are no angles in this diagram, the distances are all nice and helpfully laid out for us. So taking moments about A, in the clockwise direction around A we have just the 300 Newton force So 300 newtons times 2 meters, so that's that distance of 1 plus that distance of 1 makes that perpendicular distance from the axis equal to 300 times 2. Okay, and that's going to be equal to t, the anti-clockwise moment, t times 1, and that gives me t equals 600, which is as they asked for. X and Y then, let's look at X. Well, X, as shown in the diagram here, is the only horizontal force, external force, acting in the system. There is no other horizontal external force here. So that means that X has to be 0. From a horizontal balance perspective, X is 0 newtons. If we resolve in the vertical direction, we have upwards the t is 600, and downwards y plus 300. That's all the external forces in the system accounted for. So y is equal to 300 newtons in this case. So we have our answers there. Marks for this one, a single E mark for t equals 600, and then a B mark for x equals 0, an M mark, a method, and an answer mark for y equals 300 down here. Next part of the question asks us to draw a diagram showing all the forces acting on the framework and the internal forces in the rod. What I've done here is transfer this diagram from the previous part of the question. Obviously, you would need to redraw this if you were doing this as part of the exam, so just be aware that I'm shortcutting slightly by having this diagram already here. So I'm going to start off by getting rid of a force. We know that x is equal to 0, so I'm going to take that out. I'm going to replace the t newtons here with the 600 newtons that I know exists, and I'm going to replace my y newtons here with 300 newtons downwards, which I know to be the case there. And that covers all of the external forces. We have our 300 newton weight here, 600 upwards, 300 downwards here. So now we need to look at the internal forces on the diagram, and this is easiest done by just taking each of the vertices of the framework one at a time and applying a little logic to how that's going to be used. So I'm going to start down here at C. Now at C, I know that I have this downward force here at the weight of 300 newtons, and that means that I have to have some kind of tension in rod CD in order for there to be an upward force at C to balance that weight downwards. So I'm going to call this tension TCD, and that must be equaled by a similar force acting on D at the opposite end. In order for the rod not to stretch, it must have constant tension throughout. Take a look next at rod BC. Now TCD here, my tension in this rod, has a horizontal component that goes right to left. That means it must be counteracted by a horizontal component in BC going left to right. In order for C to be in equilibrium at that pin joint, we know that this force needs to be a thrust or a compression in rod BC. And again, that's reflected at the opposite end of the rod. The same force is applied to B as is applied to C, or the same magnitude of force. Okay, so moving on from there, next I'm going to come up here to, actually no I'm not, yes I am, I'm going to come up here to point D. Okay, so the pin joint at D here, no I'm not, sorry, I'm going to work at B first, my mistake. Okay, so looking at B here, we have a thrust going right to left acting on B, and that has to be counteracted by a horizontal thrust. That's got to come from rod AB. So the force in rod AB must also be a thrust in order for it to have a component that overcomes the thrust in rod BC. So we've got a thrust here, and that gives us a reflected value of the thrust at A. Okay. We can look, we haven't quite finished at B yet, so looking at B again, there is a vertical component to the thrust in AB, which would need to be counteracted by a vertical component in BD. So BD in this case is going to be in tension. So TBD is a tension, and that's going to pull down on D. There. Okay, so this enables us, this gives us enough information now to be able to finish off the last two pin joints. You can see here at D that we have downward components of the forces in TBD and TCD. They're going to be balanced by the 600 Newton force upwards, but the TCD tension here has a horizontal component going left to right, which means that there must also be a right to left force in AD to counteract that. So TAD is a tension in AD. And again, its partner at the other end must be equal and opposite in order for that rod to remain in equilibrium. Okay, so 2 marks for all of those. 1 mark for the external forces, the 600, 300 and 300 here. Remember, you'd be redrawing the diagram yourself. And a second B mark for the internal forces in here. Okay, so you can see in this next part of the question that I've actually redrawn those forces onto the diagram ready to go. Oh, need to take out X. I need to change T to be 600 newtons, and I need to change Y to be 300 newtons here. So next I'm going to calculate the internal forces in the 5 rods, and I need to indicate whether each one is in tension or in compression or thrust. So let's just work through stage by stage and see what we get for that. Before I start working through, I'm going to add an angle into the diagram here. If you can see this triangle here, it's right angled. Triangle BCD is right angled. It's got an opposite of 1 and a hypotenuse of 2 here, which means that this angle is helpfully a 30-degree angle in here, and similarly in triangle ABD we've got a 30-degree angle in there, which is going to make our calculations a little simpler. Starting then let's start at A. So considering the forces at A, if we look in the vertical direction, the only forces acting at A in the vertical direction are the 300 Newton force downwards and a component of TAB. Remember, this is 30 degrees in here. So TAB, just looking at the vertical balance, vertical balance at A, TAB cos 30, cosine 30, is going to be equal to the 300 Newton force downwards. That means that TAB, actually I'm just going to do that on the same line just to leave myself plenty of space there. So TAB, just using cosine 30 as being root 3 over 2, that's going to give me TAB is 200 root 3. And just to make a note there, we said that that had to be a thrust, so I'm just going to put C in brackets here, C for compression in that case. Okay, also at A, but this time horizontally, so let's just say this one is vertically at A but working horizontally this time, we've got all of TAD must be balanced by a component of TAB, and it's TAB sine 30. So that means that TAD, just balancing those forces there, is going to be 2 lots of, is going to be half of TAB, so 100 root 3, and in this particular case it's pulling away from A and away from D, bringing that rod together, so that's going to be in tension. Okay, so TAD is a tension. Okay, so let's move ahead from there. Let's take a look now at point B. So we know at point B, we know this force TAB here. That's going to enable us to find TBC and TBD. So let's first of all work horizontally at B. So working horizontally at B, we've got TAB sine 30 is going to be equal to TBC. So TBC is going to be 200 root 3. I'm sorry, I've made a mistake there. 100 root 3. Apologies. Okay. And again, looking at the diagram, you can see here that TBC has to be a thrust because that rod is in compression, so put a little C to represent compression. After that, vertically at B, we've got 1, 2, 3, 4, 5 forces to find, so we've done 3 out of the 5. Vertically at B, we've got TAB again, but this time cosine 30. Downwards, that's going to be equal to all of TBD upwards. So TBD is going to be TAB times root 3 over 2, which is going to be 300 newtons. And again, we've got TBD in the diagram here shown as a tension. And finally, let's choose one last point to work at. Let's consider C. And if we work in the horizontal direction at C, could also work in the vertical direction, but it would mean using 3 forces instead of 2. So if we just work in the horizontal direction, then all of TBC, which we already know, is equal to TCD sine 30, which gives me TCD is going to be twice TBC, so 200 root 3 newtons, and TCD we know again is a tension. So we'll give a little T in brackets there, and I'm just going to make sure that that's clear. C means compression, and T in brackets means tension. Just so it's quite clear. There's an A mark for finding the first of these values, and then follow-on marks for the remainder of the values, and a further mark for the compression versus tension decisions right the way through. There's a B mark for getting the angle and the ratios, an M mark for attempting an equation at the joints, and an M mark for at least one correct calculation. Okay, so the last part of the question now, a vertical wire is going to be attached at B instead of at D, but the framework is still in equilibrium. We have to make no further calculations, but we need to state which of the 4 rods have the same internal forces and which ones don't, and explain why that's the case. So I'm just putting my, I need to cross that force out altogether, so my 600 Newton force is now applied down here at B. Okay, it's still got to be equal to 600 newtons for this to remain as it is. So how do we decide what's changed and what hasn't in this particular case? Well, if you take a look at any of the pin joints on the outside here, you can see here at A, nothing's changed. The same results apply right the way through in terms of external forces. So the equilibrium statements for A and C are identical because the external forces are still identical. So that means anything connected to A or C is going to have the same force in it. So unchanged, the same internal forces AD, AB, CD and BC are all unchanged. Only BD is going to be affected. So let's take a little closer look at BD. We saw in the previous part of the question that AB is in thrust with a force of 200 root 3 newtons, and BC is also in thrust in here, so there's a thrust in that direction. There's also going to be a force then in BD, and I hope it's reasonably easy to see that that force becomes a thrust. So I'm going to call that TBD. In there, it's actually my new TBD. Because that acts vertically, I'm not really interested in what the value of the compression in BC is. I can just work vertically now. So at B, resolving in that vertical direction, upwards, I have my 600 newtons. downwards I've got all of TBD plus 200 root 3 cosine 30, and just rearranging that gives me TBD is now 300 newtons, and as I say, it is a thrust or compression, thrust or compression in that particular section of the rod. Just checking the marks on that one. There's an E mark for, there's a B mark for giving the rods, naming the rods that have their forces unchanged. There's an E mark for giving the explanation for that, which I should really have written down. So external forces unchanged, which implies equilibrium at A and C unchanged. Sorry for not writing that in earlier. There's an E mark for that. There's a method mark for the equilibrium calculation at B, and an A mark then for that last part. Okay, which brings us to the end of this particular section. I hope that you'll take time to go and have a look at the Further Maths Support Programme home website at www.furthermaths.org.uk. There are lots of other useful resources and ideas, events and activities, CPD, etc. available on that site, and I hope you find them useful. Thanks very much for watching, and goodbye.